Number 2, directly proportional to so we want this current element is of length dl here. AB has length dl. We want to find magnetic field at the point P due to this current element. This current element, remember, it is not infinitesimally small, but its length we take as dl, and distance of the point is considered from the midpoint of the current element. You should remember, okay? This is the midpoint of current element from here at a distance r. The strength of magnetic field at this point is directly proportional to the current passing through the current element. This is number 1. Number 2, that dB proportional to dl. Greater the length of current element, greater is the magnetic field strength. Its value depend on the strength of current. This dB is directly proportional to sine of the angle between two directions. Which two directions? This direction of current element and the radius vector. Okay? And this dB is due to the current element, no? It is proportional to, inversely proportional to square of separation. Okay? This inverse square law is true for gravitation, inverse square law true for electrostatics, inverse square law going to be true for electromagnetism also. Okay? And where there is inverse square law, the force going to be conservative. Conservative force means what? In a loop, total work done will be 0. That will explain one by one. First, let us know this Biot-Savart law. It is found due to this small current element at a distance r from midpoint of the current element, which is directly proportional to length. Greater the length, greater is the magnetic field. So if you consider whole wire, magnetic field will be more at the point P, and it depends on current. If current more, magnetic field strength will be more. This we are considering, it is continuation of the previous class where I showed you the strength of magnetic field due to current carrying wire. Okay? This dB is proportional to sine of the angle between two directions. dB is proportional to 1 by r square. Let us combine these 1, 2, 3 and 4. Combining 1, 2, 3 and 4, we get dB proportional to I dl sin theta by r square, or dB equal to k into I dl sin theta by r square. This k can be expressed in terms of electromagnetic unit of current, but will not do it. It is obsolete nowadays. No one define EMF of current. Will define SI unit only, that is in terms of current ampere. Okay? That SI unit will be used. Strength of magnetic field unit already we got. So this K is a constant, that its dimension can be expressed in terms of strength of magnetic field, length and current. This K in SI unit, K equal to mu 0 by 4 pi. Okay? This mu 0 is like E0 in electrostat. What is E0? That is permittivity of free space. What is mu 0? It is called permeability of free space. Permeability of free space is mu 0. Its value is 4 pi into 10 to the power minus 7 Tesla meter per ampere. You can write this way, 4 pi T M A inverse, like this, Tesla meter per ampere, unit, minus 1, obvious, 10 to the power minus 7, yes, it is 10 to the power minus 7, 4 pi into 10 to the power minus 7. So this scalar form, if you write, scalar form is going to be dB equal to mu0 by 4 pi I dl sin theta by r square. Okay, this is experimental observation. Theoretical basis Biot-Savart law don't have, and that theoretical basis is there in Laplace's law. Nowadays we know it in terms of this experimental physicist Biot and Savart. But initially it was invented by Laplace by mathematical treatment. He was a mathematician. It is Laplace's law. We studied in our time Laplace's law. Nowadays people say only Biot-Savart law, because experimentally they established. Okay, whatever, this strength of magnetic field due to current carrying conductor we need to put in a mathematical form. Mathematical form means to get the direction. You have to perform the experiment. Here it is observed that the strength of magnetic field at the point P is perpendicular to the plane of paper, dot going into the plane of paper. Okay, this is experimental observation, and this is in accordance with all we have studied before. Okay, so this dB is perpendicular to plane of paper and directed inward. dB vector is perpendicular to the plane of paper and directed inward. Okay, dB vector perpendicular to plane of paper and directed inward, not outward. Okay, so let us try to put this formula into mathematical form so that this can be decided from there. I just show you, if I keep the finger, thumb of right hand along the direction of current, and imagine that my fingers are long enough to reach the point P, then magnetic field is along the direction in which finger curl. Okay, so from there we can write the vectorial form. Once more I draw the same diagram here. This dB expression also I am writing, but using vector. Crossed magnetic field, dB equal to mu0 by 4 pi I dl cross r cap by r square. This angle is theta. This one we stated as theta. This is the direction of unit vector r cap, and direction of current is this I. This was the current element AB of length dl. Why dl cross r? dl to r. Why it is directed that? Why we are saying that it is with dl cross r? I told you experimentally it is found to be perpendicular to plane of paper and directed inward. The cross product concept says that if this is r vector, this is dl vector, dl to r, if we curl, then thumb going into the plane of paper. It is in accordance with the direct experimental observation. So we will never write r cross dl, it will be dl cross r. Clear? So dl cross r is perpendicular to plane of paper, r vector directed this way. We can write r vector is r divided by r. So dB vector will be what? Mu 0 by 4 pi I dl cross r divided by r cube. Okay, this is Biot-Savart law, and you can get the direction by using the right hand thumb rule. For right hand thumb rule, we place the finger along the direction of the current carrying wire, then thumb along the direction of current carrying wire, then the fingers, the direction in which they curl the other fingers, that is the direction of magnetic field. So if I give you a straight current carrying conductor this manner, so what do you expect magnetic field? What do you expect magnetic field here? Here, here, here. These points are enclosing the loop, enclosing the wire, and the wire passing through this center of circular path. Then at every point, this direction of magnetic field will be tangential. So we put the arrow this manner. This is the direction of magnetic field. That's why lines of force is circular. At every point, you can get the direction by using right hand thumb rule. Along the direction of current thumb, then fingers curl, that is the direction of B. So B directed this way, B directed this way, B directed this way. In CBSE board, derivation due to this long straight wire is not in syllabus nowadays, but we will be doing it in this class as a problem. But know your syllabus first. This application of Biot-Savart law, you will find, CBSE student will find in one case only, that is magnetic field due to a circular current carrying wire. We will solve this one as a problem. So how the direction is tangential to circular path, you have understood, isn't it? Now let us find one application we will do and one problem we will solve. Application, this is in for boards. This derivation you need for boards. Application, to find the strength of magnetic field on the axis of a current carrying circular loop. To find the strength of magnetic field on the axis of a current carrying circular loop. On the axis. Once more, I just remind you this part. You may be confused in finding direction of electric field many times. Then DLR concept, if you understand, it's fine. Otherwise, this A cross B vector is perpendicular to both A and B, that you know. So DL cross R will be perpendicular to both DL vector and R vector. Clear? So let's see what happens there in case of circular current carrying wire. It's a circular current carrying wire. We are going to find the strength of magnetic field on the axis of this circular current carrying wire. Okay, on the axis. This is the axis, imagine. Okay, and direction of current is this. What is the concept? How do you find it? You did it for current element only. Now, if we can do it for current element, then for the whole wire we can find by integration. We are going to use method of integration. So, to find strength of magnetic field at the point P on the axis at a distance x from the center of the circle we divide it into infinite number of parts. We divide the wire into infinite number of current elements. Okay, this is a current element of length dl. Due to this, we want to find magnetic field at P. This is the radius vector. Radius vector joining this current element midpoint to the point P. This has length dl. Now just tell me one thing, just this three-dimensional concept, no? What is the angle between dl and this radius vector Vp? Vp is the radius vector, no? What is the angle between this current element? I have taken a bigger diagram. You can see that clearly this current element and this radius vector. What's the angle between these two directions? I'm not drawing it full. Just tell me what's the angle. You can use your hand key and just check in what direction the magnetic field will be directed there. First you tell me what's the angle between this current element and this point P lies here and this is the radius vector. Okay? Don't you think that this thing is going to be tangential to this part? So angle between current element and radius vector is going to be 90 degree. Agree or not? Actually this angle between the current element and radius vector, this is the most important part. The angle between AB is the current element here. This is the current element. Angle between AB and R, this is the direction of R, is 90 degree. Okay? So method is very clear. We imagine that it is divided into infinite number of small parts. AB is a current element and there is a symmetrically opposite current element also. This is symmetrically opposite current element. You can recognize the way you did in electrostat due to circular current carrying wire, circular charged wire. Same way here. Now, what is the direction of magnetic field at P due to this current element? This is R vector, dl vector. Explain clearly. dl is along AB. So magnetic field, I told you it is perpendicular to both dl and R. At this point what I am getting? No dl is there. There is R only. So magnetic field will be directed this way. Isn't it? dB vector will be directed this way. It is perpendicular to R vector. dl this way. You can imagine the dl to R if I take, if we curl the fingers of right hand from dl vector to R vector, it is going like this. dl is along the circumference of circle. No. This is the current carrying loop in my hand. This is dl and this is R. So dl to R if we rotate, then thumb, extend the thumb that position. Or you take the current carrying wire at the position of P. Then this is the direction of rotation of my finger. So thumb is going to be perpendicular. That's why it is taken in that direction. Okay? So dB vector is perpendicular to R here. Now this dB has two components. One component this way, the other component this way. Okay? If I have taken this angle theta, then this angle going to be theta. Isn't it? So this way component will be dB sin theta and this component will be dB cos theta. Isn't it? Magnitude of dB you take here when writing component. dB sin, dB cos. Can you tell me what happens due to symmetrically opposite current element? If you join this, what will happen? Again the same manner, dB vector will be directed this way. It has two components, this way one component and the other one adding dB sin theta. So this is dB cos theta. So these two components get cancelled. All the current elements contributing dB sin theta part only, isn't it? So we'll proceed now. Magnetic field at P is this point, P is here. Magnetic field at P is due to the component dB sin theta only. dB cos theta symmetrically opposite, they get cancelled. Clear? dB cos theta has no contribution to the magnetic field. Magnetic field at P is due to dB sin theta only. So let us write the expression for dB first. Now we are writing magnitude. dB is what? mu0 by 4 pi. We will write magnitude only because we know the angle. That angle is 90 degree, I have specified already. So dB mu0 by 4 pi I dl sin 90 divided by r square. Okay. So dB sin theta equal to dBx. It is along x axis only. dBx is dB sin theta. This is going to be mu0 by 4 pi I into dl. dl means, okay, dl you keep there, dl sin theta pi r square. What is sin theta over there in the diagram? This part is A, this part R. So sin theta is A by R. Just put it there. So dBx equal to mu0 by 4 pi I dl A by R, and this is R square. mu0 by 4 pi IA by R cube dl dBx. dBx only exists. So B net is equal to Bx. That is obtained by integrating this expression over the whole loop. mu0 by 4 pi IA by R cube dl. Clear? But dl, if you add, what do you get? The whole circumference of the circle. So this you write. So B at P is B net is Bx. This is mu0 IA by integration dl for the whole wire. For the whole wire whose radius is A, sigma dl or integration of dl going to be what? That is circumference. Circumference is 2 pi A. Put it there. mu0 IA 2 pi A by 4 pi R cube. Understand? So B at P is mu0 I square by 2 R cube. What is R cube here? they put in terms of known quantities. R is assumed 1, but we have assumed A and X. So you can write both R square and R cube. What is R square in the diagram? R square is A square plus X square. So R is A square plus X square to the power half. So put it there. Mu 0 I A square by 2 into A square plus X square to the power 3 by 2. Clear? This is for one turn of the coil. Coil normally, if you go for practical application, has several turns. Okay? This is for one turn only. If the coil has n number of turns, then magnetic field at P will be mu 0 Ni square by two into A square plus X square to the power 3 by 2. Okay? Clear? Now the question is, what is the value of magnetic field at the center? At the center, this one sends current this manner. At the center, magnetic field is obtained by putting X equal to 0. No X is there. So magnetic field at center is given by what? You put X equal to 0. Center means X equal to 0. So B at center you take C mu 0 in I square by 2 is square to the power 3 by 2. Isn't it? So this will be mu 0 Ni by 2A. Clear? This is magnetic field due to the circular current carrying wire having n number of turns at the center of the wire. Loop. Okay? Is mu 0 Ni by 2A. Now a question arises. Practical situation, there may be semicircular wire. Then what will happen, you think? What will happen for semicircular wire? Go for finding magnetic field due to semicircular wire. Which part? This one? For semicircular wire or quadrant of circle, how to find magnetic field at the center? I mean, suppose there is a current carrying wire like this. You can remove this part right now because it will bring confusion otherwise. This is just center and radius of the path is R. You write the expression for magnetic field at the center of semicircular path. It is one turn only, and the derivation we did, it was contribution of all part, isn't it? So we can go by unitary method. The direction of magnetic field at the point O is half of the magnetic field due to whole wire. Whole wire is what? Mu 0 I by 2a, one turn, so it will be mu 0 I by 4a. For quadrant, it will be divided by 2 again. I mean by 4. Now, can you write the expression for magnetic field due to this circular arc? This one is a circular arc carrying current. What is the magnetic field at O? Current going this way. Even you can assume that through straight path also current going, the magnetic field at O will be what? They don't have any contribution here, only due to this part. This angle is given theta. Radius is r. You tell me the expression for magnetic field at O. And what is the direction? In the previous case, what is the direction? By right hand thumb rule, fix your thumb along the direction of the wire. So fingers going inward. So magnetic field at O will be inward. Here B is directed inward. This direction plays important role to find resultant magnetic field. What is the direction of magnetic field here? In this case, at the point O, what is the direction of magnetic field? That is also into the plane of paper, directed inward. What is the expression? Go by unitary method. For 2 pi angle, it is mu 0 I by 2r. For unit angle, mu 0 I by 4 pi r. So for theta angle, it will be what? For theta angle, into theta simply, isn't it? So better you remember this thing. Theta by 2 pi into B at C. Okay? Now I will be discussing one more problem like this, where this is a quadrant of circle. This is 90 degree. This is one wire. We made some arrangement. This is another wire. Current through wires going this manner. And radius of this path is R1 and the outer one R2. What is magnetic field at O? Tell Sadnik, what is magnetic field at O? This current remains the same, I only. It may differ also. How will I find? This is radius 1. Take the thumb along the direction of current wire. Fingers coming towards me. Another way you can remember. Look at the wire. If the current with respect to appear anti-clockwise, then field is going towards you. Okay? If it is clockwise, then field is going away from you. So due to these two parts, magnetic field has two different directions. So magnetic field at O, this is 90 degree we said. For the whole wire, it is mu 0 I by 2r. So for this portion, it will be mu 0 I by 8r. Isn't it? You divide the result by 4. So magnetic field at O This you take wire 1, this is 2. Due to wire 1 is mu0 I by 2 R1. This is outward. Okay. Then magnetic, this you take B1. This is outward. It's coming outward towards me because with respect to me it is appearing anti-clockwise sense. 2 R1. This part we have taken R1. So, oh sorry, it is 8R. I wrote 8R up. This will be 8R1 outward. And due to wire 2, B2 will be what? Mu0 I by 8R2. This will be directed in what direction? This will be inward. Therefore, resultant magnetic field at O B1 minus B2. Isn't it? So this will be mu0 I by 8 1 by R1 minus 1 by R2. Clear? Understood? This is just introductory sum I have asked you. We'll be doing after completing the theory portion. Next one I am going to solve this one as a problem. That is, this is a problem. This is not in CBSE. For derivation in your board examination it will never come. Okay? That I declare today. This is a problem like that. We will be using Biot-Savart law only to solve the problem. This is a straight current carrying conductor. Okay? Straight current carrying conductor AB. Its length is known or its angular position with respect to P is known. This angle θ1 and this angle θ2. This distance is R. Carrying a current I. Find B at P. It's a new problem. No link with circular. Where? This you have to find. Magnetic field at P. Due to this straight current carrying conductor. Carrying current I. Okay? You can take this one. This distance you take. R looks, it is a variable quantity. Better you take it as A. This PM is A. So from the wire, it can be anywhere. P point if you take at the extremity, then θ1 going to be 0, θ2 will be there. If you take infinitely long wire, then θ1, θ2 will be 90 degrees. So this case, if we are able to derive magnetic field at P, we can consider all the cases here. You understand the diagram? See how to find the magnetic field here. We are going to magnetic field at P due to this current carrying conductor. What we will do here? We will divide into current elements. This is a current element PQ. Oh, this P is already in use. Sorry, you take this current element XY and join X to P, join Y to P. Okay? This angle with theta Then this also theta, because it is current element, no, very small part. This angle is also theta. XY is the current element. We have taken XY as the current element. Okay. Find magnetic field at P. This one is phi. This part is phi. This one is d phi. Okay. Write the expression for magnetic field at P due to XY. Answering this way. Magnetic field at P due to XY, this current element of length dl. What is the law? Biot-Savart law will be using dB equal to mu 0 I dl sin theta by r square. Am I correct? Done? R is this distance. I did not write it here. This xp r, yp also r. Okay? So dB is mu 0 ideal sin theta by r square. Normal. There is no problem in understanding this, because with current element the direction making an angle theta, that's why sin theta. I want to cover the whole where AB, so theta doesn't help. I have to go for phi. Phi changing from this theta 1 and that theta 2. So let us express this whole thing in terms of phi. How to? So my effort will be there like this. I'll be drawing a perpendicular here. Draw a perpendicular here. X to T is a perpendicular. Don't forget that this angle is theta. Xt is a perpendicular. Draw xt perpendicular to xt, no, sorry, yt. Yt perpendicular to xp. So yt equal to xy sin theta, and yt can also be written because it is small, r d phi. So these two implies that dl sin theta equal to r d phi. This is one step. We found dl sin theta in terms of r d phi, but r is a variable quantity. Let us express that also in terms of phi. How to? Mu 0 I dl. Oh, dl sin theta we got. Substitute there. R d phi by r square. Acha, this is mu 0 by 4 pi. No one reminded me. Mu 0 by 4 pi is there, no? It is Biot-Savart law. Mu 0 by 4 pi ideal sin theta by r square. Mu 0 by 4 pi. R getting cancelled. It is mu 0 I by 4 pi d phi divided by r.
Sir,
Yes?
where is the phi?
Phi is there. This is phi. This is d phi. Shown in the diagram. MPy is phi, ypx is d phi. Because I have to cover the whole wire. No, theta doesn't help. Theta helps us to just figurize Biot-Savart law. We have to get in terms of phi. How to? So mu 0 by 4 pi d phi by r. Here phi and r both are variable. You express r in terms of phi, then it is done. We have taken a fixed distance a over there. So use this concept. here in this diagram, in the diagram we get A by R cos phi, isn't it? Use the fact here. Use this fact here. We are writing expression for dB. dB is this. So dB is mu 0 I by 4 pi 1 by R. What can you write from here? See, I have written. I am writing again. A by R is cos phi. So 1 by R is what? Cos phi by A. So put cos phi by A and d phi is there. Clear? You all understand? Now net B will be what? That is integration. B will be integration of mu 0 I by 4 pi A cos phi d phi. You have nothing to think about this part because this is constant. Phi, limit of phi. Limit of phi will be what? With phi only you are covering the whole wire. If you rotate this manner, upper part cover. If you rotate this manner, the lower part is covered. One is in clockwise sense, the other one is in anti-clockwise sense. So one direction of angle negative, the other one positive. So you take the angle below it as negative, minus theta 1 and this is theta 2. Clear? So B will be equal to mu 0 I by 4 pi A cos phi integration is sin phi minus theta 1 to theta 2. This will be mu 0 I by 4 pi A sin theta 2 minus sin minus theta 1. So B will be equal to mu 0 I by 4 pi A sin theta 1 plus sin theta 2. And now this is a very important tool for you for all competitive exams. For a straight wire, if you can do it, you can do it for a long straight wire. You just tell me how to do it for long straight wire. Can I write theta 1, theta 2 for it? Long straight wire extends up to infinity both the way. There is no boundary over there. It is not stopped here. Continuing. P is the point. This is A. I want to cover the whole wire. Then theta 2 for upper part going to be 90 degree. Theta 1 for the lower part going to be 90 degree. So you write this one as a case. For an infinitely long wire, theta 1 90 degree, theta 2 90 degree. So B is going to be mu 0 I by 4 pi A sin 90 plus sin 90. So it is 2 mu 0 I by 2 pi A. This is very important. We will derive this by using Ampere's circuital law also. It is mu 0 I by 2 pi A. Clear? So magnetic field at a distance A from infinitely long wire carrying a current I given by this. This P is arbitrary. This is not at one end of the wire, but P may lie at the end of wire also. This is infinitely long wire, XY. But X is fixed, Y is not fixed. P lies here. Can you tell me what is the value of magnetic field at P if this length is A? Same length, only P corresponds with the extremity of the wire. So magnetic field here, if the point P lies or corresponds with one end of the wire, then B equal to what? See, this you have to keep in your mind. Theta 1 is 0 and theta 2 exists 90 degree. So put here theta 1 0 degree, theta 2 90 degree. So B at P going to be mu 0 I. What is the expression? Mu 0 I by 4 pi a. Sin theta 1, that is sin 0 plus sin 90. So B at P will be clear? Understood? This is the expression for magnetic field due to a long stator. I just show you one area of application. Okay? One area of application, many applications will be done later, but right now you are going to find the strength of magnetic field at the center of wire of this shape, triangular shape. For your simplicity of calculation, I am taking equilateral triangle. ABC, carrying current I here. You have to find magnetic field at O, that is center of the triangle. Here all three centers will be the same, isn't it? All three, I mean incenter, circumcenter, orthocenter, centroid, whatever you say, all look similar. Look, no, all are similar. Really, they are similar. You have to find magnetic field at the center of this current carrying loop. This is also a problem. Now this problem will not arise in your CBSE board paper. It was there in 2 years back also. Now it is not in CBSE. For interns we are doing that. So I am clearly telling you what you need to practice for board. This is not for board. This is for your NEET or JEE exam only. So what is strength of magnetic field at O? You can use symmetry. For the wire BC, whatever magnetic field there, for CA it will have the same length. For AB also. Isn't it? At which point you are going to find? You are going to find at O. This be the perpendicular distance. O to M. For one wire, let us do. Let us find B at O due to one side. Due to AC. Is what? This angle is 60, this one also 60 because total angle 120 degree. You agree or not? So B at O due to AC will be mu 0 I by 4 pi A sin pi by 3 plus sin pi by 3. Because all those directions minus plus we are not thinking, just sin theta 1 plus sin theta 2. Whatever theta 1 is there, you put it. No need to consider angle convention over there. Clear? So it will be mu 0 I by 4 pi A 2 sin pi by 3. So B at O will be this, root 3 mu 0 I by 4 pi A. Clear? Now for the whole wire roller additive, see magnetic field coming out, the direction of current I showed. If you fix a thumb in that direction, it is coming out. So this is outward, perpendicular to plane of paper and directed towards me, because current appearing, I told you, if it appears anti-clockwise, then magnetic field will be directed towards me. So B0 is root 3 mu 0 I by 4 pi A, it is directed towards me, and this field is additive. Net field is due to all three sides, that B0, B0 and B0 outward. For all three outward, by use the right hand thumb rule, you are getting 3B0. 3 root 3 mu 0 I by 4 pi A. Okay? If I tell you to do it for a square, what will you do? For a square wire, it's a square loop. This is a square loop. We have to find magnetic field at O. It is carrying a current I and length of side is A. Just for idea. You understand what I am going to do? We will find magnetic field at O due to this square loop. Length of side is A. So again, you find it due to one side. Just draw perpendicular. OM is the perpendicular here. Then theta 1 is what? This is theta 1, theta 2, theta 1 45 degree, theta 2 also 45 degree. So B going to be what? Mu 0 I by 4 pi A sine 45 plus sine 45 multiplied by 4 sides. So multiply the result by 4. But what about this A? One thing, in the previous sum also I did not specify A. What is A? A is not this A. I am sorry for that. This is R actually, no? This R you have to clarify. What R is there? This is not A. A is the length of side. This R is what? This is R. This R is actually 1/3 of height. That is 1/3 of root 3 by 2A. So it is, he'll be putting that only. R equal to, please make this change. Okay, you could have asked me. A is the length of side here, not that part is not A. The same manner, length of side is A here. What about the perpendicular distance here? Very easy to say, tell. This A, this is not, this you don't take A, you write A dashed. This A dashed is half of A. You agree or not? That multiplied by 4. Because this, no, this to this, length of side is A. This has to be equal to A by 2. So there it will be 4 pi into A by 2, 2 sine 45. Clear? Understood? This is just introduction, that how to use Biot-Savart law to find the magnetic field due to straight wire, final length, due to long straight wire, and due to combination of wires, due to many wires also we can find. Clear? So we will be solving many problems, but let us know what is Ampere's circuital law. Then we will go for solving problem. This chapter, today's class is devoted to find magnetic field due to a long straight wire, due to straight wire, due to circular wire, and due to solenoid. Solenoid also we can find by using Biot-Savart law only, but it's a difficult calculation for you nowadays. Don't take the stress of deriving Biot-Savart law. We will do it by using Ampere's circuital law. Okay? Let us know what is the law. Circuital law. That I am writing secret here. Okay? Ampere's circuital law. What is that? This is an easier way to get magnetic field. This is the law with some limitations also. Biot-Savart law or Laplace's law, whatever you say, it can be used for solving many problems. But here, Ampere's circuital law has limited application. But this is easier than Biot-Savart law. Although we can prove Ampere's circuital law by using Biot-Savart law, but you will find interest in complicated case without integration, avoiding integration, how to find the magnetic field. Here actually many wires are there. Finding magnetic field by using Biot-Savart law will be difficult at a point. We will do it solving problem like that. This wire carrying a current I1, infinitely long wire I2, and this is I3. We need to find magnetic field at any point. I am taking this point, P say. How to find? We will find magnetic field due to this, magnetic field due to this, magnetic field due to this, then vector addition or subtraction. But Biot-Savart law we can find it very first. Know what is Biot-Savart law first. These are the wires. P is an arbitrary point. Through this point we are drawing a loop. Jump. We are drawing a loop through the point P. Closed loop. Okay? We can relate these currents with the resultant magnetic field. Suppose the resultant magnetic field at the point P be B, and this a small elemental portion PQ, this has length dl, PQ length be dl. Okay, we are going to state Biot-Savart law first, and then we will find the Ampere's circuital law first, then we will find the application. Here PQ is dl. Resultant magnetic field at the position of PQ is B, and angle between PQ, this elemental part, and this direction of magnetic field be theta. Then you define a quantity, which is called circulation of magnetic field. This term we are going to state, circulation of magnetic field. This is defined as B dot dl. Dot product between B and dl, this is called circulation of magnetic field. We want to write net circulation. The net circulation of this B, you can write here that B at a point is the resultant magnetic field. Why resultant? Because many wires are there. Resultant field will be there. Resultant magnetic field is B. Then B dot dl is circulation of magnetic field. We define net circulation of magnetic field, which is nothing but this loop integral B dot dl. Okay, net circulation of magnetic field is B dot dl, summing all those things. Then Ampere's circuital law is what? What is the rule of Ampere's circuital law? You got net circulation after definition. Ampere's circuital law states that net circulation of magnetic field along this imaginary loop is equal to mu 0 times the current enclosed. Current enclosed by the loop. Ampere's circuital law we are not going to prove. We will assume that it is true. Proof is not there in board exam. Proof is not there for competitive exam, but you must learn it properly. There is already a point of confusion arise. Currents are there. Should I take all three positive, or some of them positive, some of them negative? How can I decide the direction of these currents? What you have to do there, you have to put an arrow along the loop. I am not specifying any direction, clockwise or anti-clockwise. It's your choice. Okay? I am putting arrow this manner. This manner. You put an arrow. This is a step here. Curl the finger of your right hand other than thumb along the direction of arrow. Thumb gives the direction of positive current. Got it? So I am telling you this in steps. To decide the sign of I1 or I2 or whatever. We have taken 3 only here to decide the sign of this in Ampere's circuital law. Here I is the net current, no current enclosed by the loop. So what we will do? Step 1. Step 1 is what? Put arrow along the loop, either clockwise or anti-clockwise. Put arrow along the loop in a direction. It may be clockwise or anti-clockwise. It may be clockwise or anti-clockwise. Put arrow along the direction of loop in a direction which is clockwise or anti-clockwise. Step 2. Step 2 will be curl the fingers of your right hand along the direction of the arrow. Curl the fingers of your right hand, but this will be except thumb. Except the thumb in the direction of the arrow. Other fingers in the direction of arrow. Now decide which one positive, which one negative. These two steps you have done. Step 3. Step 3, thumb gives the direction of positive current. Alright? Thumb gives the direction of positive current. Otherwise it will be negative. Opposite direction will be negative. So let us apply immediately here in this problem. Thumb gives the direction of positive current. So in our problem, how do I apply this concept here? The Ampere circular law for this, B dot dl is going to be this loop integral along the loop, that's why. B dot dl equal to mu0 into current enclosed. If I put the fingers along the direction of arrow, thumb will give the direction of positive current. So I1 positive, I3 positive, but I2 opposite. So done. This is Ampere's circuit law. This understanding is required by you. Okay? When there are many currents, due to those currents we want to find magnetic field at a point, that can be done with the help of Ampere's circuit law. Let us go for one application of it. Application of the law. One application only. Other side give you as homework. Application. That is magnetic field due to a solenoid. Magnetic field due to a solenoid. What is that? Solenoid, this is a new term here. Seems that it is a new term, isn't it? Solenoid is a cylindrical helix which is obtained by winding large number of turns of an wire on a cylindrical framework which is made of some insulating substance. Which is made of some insulating substance. This core of solenoid is, it may be cardboard, it may be some material like plate, we make that material, that is what? China clay. The core of transformer, this cylindrical part, this core may be made of pitchboard, wood, china clay, etc. Winding you have understood. This solenoid is used to produce strong magnetic field inside the solenoid. Outside it, magnetic field will be zero. Be out, outside. Zero, but be in at any point along the axis or inside the cylinder, it is very strong. But if you don't send current, this is not possible. You send a current in a particular direction, coming out this way, going in this way. It is happening, no? Going this way, then coming out. Okay? Due to this solenoid, you want to find magnetic field inside or outside. Outside, I told you 0, but we need to prove it. We need to prove this. How to? Let me take a beta diagram. Beta diagram, although not possible by me, but I am trying. One side, this is the other side of solenoid. Here I am putting dots. Here I am putting crosses. This winding you have seen, it means what? Current is coming here, like that. Okay, the same solenoid I have taken here, but for understanding purpose, I have taken it this way. Okay? I can just take one more part. Just to understand, it is going in like this and coming out like this. Now, yeah, this is the skeleton diagram of solenoid. So these currents are coming out this way, and this is entering, coming out, entering, like that. Okay, entering, coming out, going, coming out, entering. It's like this. Okay. Now here, what is the direction of magnetic field? It will be, what are the magnetic lines of forces direction? It's like this. At this point, it's like this. At this point, it will be like this. Every point here it will be like this. But here it is going in. So, it will be like this. Here, like this. Because currents are entering here, no? Currents are entering. So, it will be like this. Now, all these wires, they have magnetic field. So, inside solenoid, what is happening? Magnetic field lines are going this way, or going this way. Am I clear? Why deviation like this you understood? Because here it is directed this manner, no? See the arrow? That's why this line of force will go this way. And this is very strong. Outside, what is happening? Outside point, this magnetic field, this due to these wires, magnetic fields will be directed this way. And due to this other part, it will go like this. So they get cancelled. Magnetic field B out. That's why 0. This happens for a tightly wound solenoid. So for a tight, we consider only tightly wound solenoid. For a tightly wound solenoid, B out 0. B in is very strong. Okay? And now we have to find magnetic field inside. B out, that these lines of forces have tendency to make circular loop this manner, no? And these lines of forces to make circular loop this manner. Here, No, this is not. Just a minute. Just a minute. This will be going at this point outside. Lines of force will go this way, and here, due to this. Due to this part, it will be like this. They get cancelled outside. They cannot intersect. That is also a reason. So arrow goes this way, arrow goes this way. At this point, they are interacting. So these magnetic fields, they get cancelled. Clear? Draw this diagram as small as, as fast as possible. Oh, this arrow I have taken down. It will be like this only. Then they get this way, no? This way, this way. This way it's going due to these circular loops. So they get cancelled outside. Inside they exist. They add each other. So it will be like this. Okay? Now, how to find the strength of magnetic field at a point inside? Outside, though, we have proved zero because lines of forces, they cancel. To find the strength of magnetic field at a point P inside, we have to draw a loop. Then we will do path integration, no? Circulation of magnetic field. This is the Ampere's loop. We want to find magnetic field at P. So through that point, I am drawing this loop. A, B, C, D is the loop. In what direction should I put arrow? Arrow will be directed this way. We can put it in any direction, it's up to you. If you say that no, arrow I will not take this way, I want to take arrow opposite way, take it, no problem. It will give you the same result. So along AB, the strength of magnetic field is constant. Let us calculate net circulation of magnetic field along what? Along the loop ABCD. B dot dl. B dot dl is what? mu0 into current enclosed IN. IN means current enclosed. Some data I need to provide. You assume that N equal to number of turns per unit length. Okay? And this length we have taken, ABCD is the loop where rectangular loop, AB is of length L, BC is of length B. So B dot dl is mu0 IN. Per unit length, how many turns are there? Per unit length for this one, how many turns are there? N. So over this length AB, how many turns will be there? Tell. Over the length AB, how many turns will be there? Number of turns along AB will be equal to N into AB. N into L. N into L, because that length we have taken L, so it will be N into L. So I enclosed will be what? I enclosed will be what? They all are enclosing current. In this problem, I enclosed is going to be what? N into L into I. Am I correct? AB length is L. Per unit length, how many wires? N. So over this wire, over this length, N into L. So this loop including how many currents? NLI. That I have written. So B dot dl equal to NLI. So now we have to calculate for this B dot dl. B dot dl along AB plus B dot dl along BC plus B dot dl along CD plus B dot dl along DA. You understand that ABCD B dot dl I have simplified. The sum going to be what? Mu 0 NLI. Isn't it? This part is clear. Now along AB magnetic field strength same. So B we can take outside, integrate dl, or you can write one more step. That okay. I want to simplify more. You write B dl cos 0 degree over AB. This one what? B dl cos 90 degree along BC. Along CD it is outside 0. Along DA again B dl cos 90. Clear? This is mu 0 NLI. So B is a constant, it will come out. DL integration is L equal to mu 0 NLI. So B is what? Mu 0 NI. This very strong magnetic field, mu 0 into N into I, is found at the center of the solenoid. Clear? Understood?